Good evening, everyone. So, today we are going to cover the Ramsey number. Before we start, let's recall the definition of a complete graph. So, complete graph is a simple, undirected graph where every vertex is adjacent to all other vertices. So, first I use the word simple. It means that there cannot be more than one edge between two vertices, and undirected. It means there is no direction, and also there should not be loops means that there is an edge which is starting and ending at the same vertex. So for example, if I have four vertices and I want to find a complete graph, just for the understanding, even if I give them the numbering, so I make one adjacent to all three. Similarly, I will make two adjacent to all three. So there you can see that each vertex is adjacent to all other vertex. Two important observation about the complete graph is that if I denote it by kn, then degree of all the vertices in kn is n minus 1. Degree means degree of a vertex v is the number of the edges which are incidenting at v. So if it is k5, degree of each vertex is 4. And the other observation is the number of the edges in Kn is always n minus 1 by 2. So this is the number of the edges. Okay. Now let's talk about the Ramsey theory. So Frank Ramsey, born in 1903 and died in 1930. And during that small period of time, he introduced the concept or the theory, Ramsey theory. So in simple words, we can say that the Ramsey theory says that if there are six or more people, then either three of them know each other or three of them do not know each other. Or word is important. Yes. So if you think it, it makes sense. But mathematically, how do we prove it? That's more important question. And it says that out of six people, either three know each other. So either three means any three. If you pick any random three out of six people, either they are knowing each other or they are not knowing each other. You just have to pick any random three. This is what it means. So to prove it mathematically, we are going to use the concept of graph theory. So we will write it like this, that if there are six people, we'll present it as k6, and one of the k3 shows that these three know each other, and this k3 shows that they do not know each other. Let me talk into detail. So we distinguish between known people and unknown people by coloring red edges for the known and blue for unknown. Okay. So it means that if I say in K6 there is a red K3, so K3 means this. So if I give them the number 1, 2, 3, if I say there is a red K3, it means all three know each other. And if there is a blue K3, it means all three do not know each other. Yes, it means that if you consider K6, so 1, 2, 3, 4, 5, 6. So if you consider K6 and if you color its edges with red or blue randomly, yes, so there are in total, so each edge can be colored in two ways, and total n minus 1 by 2 edges are there. So 2 raised to the power n minus 1 by 2. So this is how you can color it. If you color them randomly, then in each coloring either you will find a red K3 or a blue K3. Yes, this is what need to be proved. It's not like you just make one coloring and say that, see, there is a red K3 or blue K3. It's not correct. If you have to disprove it, then you need to find a coloring where there is no red K3 and no blue K3. But since we need to prove it, it should be true for all three. It should be true for all colorings. Okay, so this is what it means. K6 goes to K3, K3. It means that no matter how the edges of K6 are colored with colors red and blue, there is always a red K3 or a blue K3. Yes, so let's try to prove it. Let us consider there is any vertex V. Since this vertex is adjacent to 5 vertex, because each vertex has degree 5 in K6. Now, out of these 5 edges, either at least 3 are blue or at least 3 are red. Yes, half of them are either blue or red. So let's assume 3 are red. You can take any of the options. So let's say these 3 edges are red. So I can mark them A, B, C, which means VA, VB and VC are red. Yes. Now I have to show that either there is a red K3 or a blue K3. Now there are two possibilities. One is none of the edges which are joining ABC are red. It means you have A, B and C. It means all of them are blue. If all of them are blue, it gives you a blue K3. Yes. And the other case is not all are blue. It means at least one is red. So it means either AB is red or BC is red or AC is red. Even one of them is red, then you can say that, for example, if AB is red, then along with VA, AB and BV forms a red K3. It means that whatever way I use to color the edges of K6, at the end I would have either a red K3 or a blue K3. Now let's see the other question. It says that prove or disprove K5. It means that if you do a coloring of K5, K5 can be easily be drawn. Then you have to either prove that there would be either a red K3 or a blue K3, or you need to disprove it, you need to find a coloring of K3 with two colors, red and blue, such that that coloring does not have a red K3 and a blue K3. To disprove, you have to show that both are not possible. Yes, so think and spend some time. Yes, so this is not correct. If you see this figure, there are two kinds of the lines are there, dotted line and the solid lines. Assume one of them to be red, the other to be blue. You can say that neither the dotted line are forming a K3 nor the solid lines are forming a K3. It means that this is a coloring of K5 which does not have a red K3 as well as a blue K3. It means that I cannot write K3 goes K5 goes to K3 comma K3. So now comes the Ramsey theorem, which says that consider any two integers m and n, pick any value, for example 15, 17 for example. So for these two integers, there is always a positive integer p such that kp goes to km comma kn. Okay, the theorem nowhere talks about that what that p would be. It just gives or talks about the existence of such a p. Yes. So mathematically the problem is to prove that there always exists such p such that kp goes to km comma kn for given m and n, and algorithmically or constructively we need to find such a p. So that again a very complex problem. Okay. So it means that the Ramsey theorem says that for the given m and n there is always a positive integer p such that if edges of kp are colored red or blue, then either there is a red km or a blue kn. The existence of red km or a blue kn is guaranteed no matter how the edges of kp are colored. The other thing it says that if kp goes to km comma kn, then kq when q is greater than p. So for example, k6 goes to k3, then k7 also goes to k3 and k3, k8 also goes to k3 and k3, and so on. And it is very easy to think about because k6 would always be, or kp is always a subgraph of kq where q is greater than p. And since it is a subgraph, so in k6, in a coloring of k6, when we have red k3 or a blue k3, then in k7 also we have such a k6. In k8 also we have such a k6. So that's why it would always be true. So now let's introduce the Ramsey number. So it says that Ramsey number, which is denoted as Rm comma n, is the smallest integer p such that kp goes to km comma k. Yes, and Rm comma n is same as Rn comma m. So for example, if we talk about k6, then we have already proved that k6 goes to k3 comma 3, and k6 is the smallest because k5 does not goes to k3 comma k3, and that's why the Ramsey number r3 comma 3 is equal to 6. Now let's try to prove r2 comma n is equal to n. So the proof is very simple. Just we need to understand what need to be proved. So we need to prove that kn goes to k2 and kn, and kn minus 1 does not goes to k2 and kn. To prove kn goes to k2 and kn, recall that k2 is simply an edge. This is k2. So now if I color all edges blue, then I have a blue kn. And if I do not color all edges blue, it means at least one edge is red. That red edge gives me a red k2. So that's why it's very trivial. In case of kn minus 1, of course kn is not possible. So in kn minus 1, if I color all the edges blue, then I don't have a red k2 and I don't have a blue kn. So this is how it can be proved. And similarly I can prove Rm comma 2 is m. So these numbers R2 comma n or Rn comma 2 are known as trivial Ramsey numbers. Now prove that R4 comma 3 is greater than 8. It means you need to prove that K8 does not goes to K4, K3. It means that you need to find a coloring of K8 which does not have a red K4 and a blue K3. Okay, spend some time and try to find such a coloring. The answer may not be unique, but I will show you one such coloring. If you see this coloring, then this coloring has red K3. Yes, but it does not have red K4, and of course it does not have a blue K3. So these are some more results about the Ramsey number, and as the number increases the problem becomes more and more complex. So for example, for r3 comma 10, k43 goes to k3 k10, k39 does not goes, but we cannot say anything about k40 k41 and k42, and that's why r3 comma 10 is still unknown. And if you want to generalize the Ramsey theorem, then the generalize can be in terms of any number of the colorings. We have just discussed for the two colorings. We can generalize for three coloring, four coloring, and so on. So for three coloring, this is how it looks like. And only one result is known for the three coloring, which is r3 comma 3 comma 3 is equal to 17. It means if you take K17 and color the edges with three colors, red, blue or green, then there would for sure either a red K3 or a blue K3 or a green K3. Okay, so you can see that as the number of the colors increases, it becomes more and more complex. So that's all from Ramsey number. Thank you.